Okay. Good morning, everyone.
Good morning.
Good morning.
I hope you're all doing well.
Yeah, sure. Yourself?
I'm also fine by God's grace. All right. So we continue the heat transfer. We started on Monday with heat exchanges. Today we'd like to go through the conduction aspect of heat transfer. Yeah. By then, do you have any question on the heat exchanges? Hello.
Hello, you can be heard.
Yeah. Please, do you have any question on the heat exchanges?
Is any question? Can be.
I think the silence means no.
Okay.
Hey,
All right. Then we can continue from here. All right. So we'll go through the general conduction equation, but I'm sorry, I won't be able to go through the proving because you asked you to prove it. So we just go through and know what the general conduction equation means, then we'll continue from there. Yeah, so when it comes to conduction, it's generally the heat transfer through a solid medium. So if there is heat being transferred through a solid medium, then we can say that the heat that is being transferred is by conduction. Yeah. So if there is no solid medium, then we can't consider conduction over there. Then when you take for convection there should be a bulk fluid which is in a bulk motion of fluid. So you can have heat transfer through a liquid or something like that to a fluid. But if the fluid is not in bulk motion, then it's not conduction heat transfer. So for convection. So for convection heat transfer to occur, there should be a bulk motion of the fluid. Yes. Okay, so when it comes to conduction, conduction is generally guided by the Fourier's law, and it states that the heat flux is directly proportional to the um, temperature gradient. So when it comes here, this is our heat flux. That is the heat that is being transferred per unit area. Is the heat flux, and that is directly proportional to the temperature gradient. And the temperature gradient is the delta T on delta X. Yes, and the constant of proportionality here is the thermal conductivity, which is represented by the K. Yeah, so the negative sign here shows that um, there is loss of heat from one point to another. Yeah, that's why I have the negative sign over here. Okay, so this equation can be represented in two dimension, one dimension, or three dimension. So the one we are having here um, is in three dimension. I hope you know what this operator means. Okay, so writing it in vector form, we can have this equation over here. So expanding this, we can just multiply this the t by whatever we are having here, so that we have the conduction heat equation in three dimension. And as I said earlier on, you can also have it in two dimension or one dimension. Okay, so we can also have the equation in the rectangular coordinates where we consider the x, y, z. They also have the cylindrical coordinates, which in this case we consider the radius. Is it coming?
Yes, I think the problem is my laptop. I'll try again. But you don't want to continue. The problem is my laptop because I was looking for single views. You know, I met this guy, Welbeck. I think I have to restart my laptop. So you don't want to continue. It's also not family. It's fine. You continue.
But this one note that you've opened. So when you open, you have to open the panel.
Yeah, yeah. It's already, I've already selected it. So
No, okay.
I think I've already selected it. So you can just draw when you get, you can just start drawing.
Okay, so you can also have it in the cylindrical coordinate and the spherical coordinate as well. Yeah. Okay, so when it comes to general balance equation, we know that accumulation is equal to the input minus output plus production minus consumption. Yeah, so in this case, we won't consider the consumption aspect of the heat. So just have only these four terms over here where you have the rate of thermal energy being accumulated should be equal to the rate of thermal energy in minus out, then the rate of thermal energy production. So there will be some instances where um, we'll consider no production or no generation. So this term goes to zero, and we can also consider steady state or unsteady state. So depending on the assumptions that you are going to do, this equation can be simplified. Yeah. Okay. Okay. So this is what we use to generate the general conduction equation. Yeah. So we have this component over here in 3D form. So we have the x direction, the y direction, and the z direction. So when you take the x direction, for instance, the heat is entering through this point and is coming out at this point. And when you take the y direction, it's entering through this point, then goes out here. Then the z direction also we have it here. Then also going out here. So we are considering the positive um axis of each of them. Okay, so the assumptions made here is that the density, the thermal conductivity, the specific heat capacity are all constant and they don't depend on the temperature or the direction. The material is homogeneous and isotropic. That is, and when we say isotropic material, it simple means the physical property does not change with direction. So at any particular direction, they are constant. Yes. Then V is also zero. That is, the solid material has zero bulk velocity. Okay, so when it comes to the thermal in or thermal out, by heat conduction, we only consider only this for now. Then by virtue of overall fluid motion, so you consider the conduction aspect and also consider the sensible heat. Yes, so we are not considering the convection or radiation over here, so only consider the conduction aspect of it. So in that case, since conduction, there should be a solid medium through which the heat can be transferred, um, and that solid medium should have a bit thickness at least for the heat to pass through that thickness to the other point. Yes. So when you consider the component, for instance, or the x direction, you can see that the thickness is this entire thing over here. From this point to this point is the thickness. So we have one surface here, and we have then another surface over here. So from here to here comprises of the thickness. Okay, so we can do that across the x, the y, and the z component. And the when you take the across the surface at x, you have change in y delta z multiplying the heat flux. So what we are having here represents the area, and when you multiply the area by the heat flux, you are going to get the heat that is being transferred. The same applies to the y and the z direction as well. So this
Let's move. God bless us with peace. From the sun. Okay. A minute, guys. I think there's an issue with the laptop. I'll get it running soon.
Alright, sorry guys, our PCs are giving us a big challenge, but we'll be fine. Okay, so when you consider both writing everything for the input and the output and substitute them into the word equation over here, you are going to get this equation we are having over here. So this represents the accumulation time, and um, this represents the heat flux, which is the input minus the output, then plus our production term over here, which is so the production here term over here is per volume. So it means that all the terms here are expressed per volume. Yeah. So taking the limit as delta x approaches 0, delta y approaches 0, and that of z approaches 0, we are going to have this term over here, this equation over here, then applying our differential equation principle to generate, we'll get our general heat transfer equation by conduction to be in this format, which is in this box over here. So in this case, all the terms have been considered. So in a case where we consider steady state, then this whole term here goes to 0 because this represents the accumulation term. And when we consider no production of heat, then this term also goes to 0. Alright, then what we are having here represents the heat flux. So this equation or this heat flux is in 3D format. So in a case where you are considering only one dimension, assuming the x direction, then we have the y and the z direction goes to 0. They only have this term over here. Yeah, so when it factorize the t out over here, we are going to get a term known as the Laplacian operator. So in that case, you can just represent that term by the sign you are having over here, which represents the Laplacian operator. So what you are having here can equally be represented in this condensed form. Yeah, so this is the representation of the Laplacian operator. So you are just multiplying it by the t to get this format over here. Okay, Max, so you can ask your question.
Please, I wanted to know when the when you were explaining the formulas, you're like the first term goes to zero. What's that term? Can you go up a bit, please?
Is it this one?
Yes, please. Where the mouse pointer? Yeah.
Okay, this term will goes to zero when we are considering steady state processes.
Okay.
Are you fine?
But then you see, when you said something, but I forgot. You said, is it the Q to the power of it? Is it three or two? You said it goes to zero. That they tell when they tell you there's no production of heat, it goes to zero, right?
Yeah. Yes.
Yes. And then I'm also asking for the one on the left hand side of the equation. You also said a term for that one.
Okay, so this is the accumulation thing, the rate of accumulation.
Okay. Oh, okay. So when
Yes.
like there's no rate of accumulation, that one is zero.
Yes, and that will happen when we have steady state processes.
Oh, okay. Okay.
So if it is on steady state, then it means this term will not goes to zero.
Oh, okay. Okay.
Yeah,
Thank you so much.
you're welcome. I hope you know what steady state means.
Yes, please.
Okay, sure, then we can continue. Okay, so we continue from here. Okay, so we are also introducing another term known as the thermal diffusivity, which is alpha and is represented by K over rho Cp, and the unit for that is meter square per seconds. Okay, so to get this term over here, when you divide through the thermal conductivity, this K term over here becomes 1, so this won't have it over here. Then this one will become per K, that is the K prime 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 over K. Then we have the rho Cp over K over here. Then we know that alpha is equal to K on rho Cp, which means that if I have rho Cp on K, that term becomes what? The inverse of alpha. So we are doing that, we are going to have this term over here in the 3D format here. Okay, so we have some simplified forms of the heat conduction equation. So what we are having here represents the general form of the conduction equation, or this, yes. So any of these, 1, 2, they represent the general conduction heat equation. So you can simplify it depending on the condition of the process. So in a case where we have no heat source, there's no production of heat, then the Q prime prime term goes to zero, and that equation will become the Fourier's equation. Okay, then when you consider steady state conditions with heat generation, then it means the accumulation terms goes to zero. So we only have the right side of the equation, and that equation is known as the Poisson's equation. Then in the case where you consider steady state conditions and no heat source, then we have the Laplace equation. Okay, so to solve this a differential equation we are having. So to solve this differential equation, you need uh, boundary and initial conditions to solve those equations. Yeah, so boundary conditions are restrictions or specifications applied at the physical boundaries of the system. Then initial conditions are specifications applied at the specific time for unsteady problems. Yeah, so when they give you the problem and you are solving it, make your you can get your initial conditions and your boundary conditions for that, and that will help you solve the differential equation you are having. So there are four kinds of boundary conditions that can be used or they are commonly used in this course. So the first one we have is temperature at the temperature at the surface may be specified, and this temperature is TW, which is mostly constant. Then we also have the heat flux at a surface that may be specified, and that's also constant. Then you can also have at a solid fluid interface, the heat flux may be related to the difference between the temperature at the interface and that in the fluid by Newton's law of cooling. So the solid part has to deal with the conduction aspect, and hi. Yeah, someone is asking a question. Can you talk? Okay, then we can continue. All right, so the solid aspect has to deal with the conduction aspect, then the fluid aspect will be governed by the convection aspect. And the law we mostly used in the convection aspect is the Newton's law of cooling. All right, so this left side represents the conduction aspect, and the right side represents the convection aspect. Then you can also have at solid-solid interface. Then the continuity of temperature and heat flux may be specified at this point. They also have the initial conditions, which are of two types. An initial time condition, the temperature or heat flux is specified at the start. They also have time goes to infinity for a number of problems. When t goes to infinity, so the steady state is reached at this point. So these are some of the conditions, or the boundary conditions and the initial conditions that you can get, depending on the problem that they have given to you. All right, so we continue from that part. So we consider steady state heat conduction in one dimension. The general form was in three dimension. As I said earlier on, you can have it in one dimension, two dimension, and three dimensions. So in this case, you are going to consider only one dimension, and also consider steady state. So when you go to the equation over there, our accumulation term goes to 0. All right, so when it comes to this topic, our objectives are to determine the temperature distribution and also to find the heat transfer rate. All right, so we'll consider problems that are related to plane geometry systems and also consider problems related to the spherical systems. Yeah, so we'll first start with the plane geometry systems. So heat conduction in a plane wall. So what we are having over here represents our wall with a thickness um delta. So the thickness is the delta over here in the x direction, the positive x direction. So we have our temperature from this point with T1 reducing to T2. So the surface temperatures are T1 and T2, and the thickness of the wall, the plane wall, is the delta over here. So the assumptions here are T is a function of the x direction, that it only varies in only x direction. They also consider steady state, then also consider isotropic material, that is our K rho Cp equal are constant. They also consider there is no heat, internal heat generation. So in that case, when it's simplified the equation, we are going to have the Laplace equation, which is this equation over here. So writing this out, we are going to have this term over here. So applying our differential equation solutions to differential equation, we integrate this term over here, and when we integrate that, we are going to have this term over here, and whenever you integrate, you have to introduce a constant. So the first integral gives us a constant C1. Then when you further integrate this term over here, you're going to have this term over here, and you're going to add another constant to it. So you have C2 over here. So solving this, you need boundary conditions and initial conditions to solve this equation over here. So when it come here, um, at this point over here, at the surface over here, we can consider when x is equal to 0. We are starting from x starts from this point. So when x is equal to 0, our temperature becomes T1, which is on this surface. And when x equals delta, that is from this point to this point, our T becomes T2. So when you consider x to be 0, we are going to have okay. So when it come here, at this point when x is equal to 0, we are going to have this temperature over here. We are going to have our T, the T here to be equal to C2. That's when x is equal to 0. This term goes to 0. This whole term goes to 0. So we are going to get T to be equal to C2. And when x is equal to delta, we are going to have our T to be equal to T2. So when you solve for C1 and C2, so you have our boundary condition 1 over here. When x is equal to 0, you have T to be equal to T1. Then solving the equation, you have T1 to be equal to C2. That is this term at this point over here. Then when x is equal to delta, we have t to be equal to t2. So in this case, we are going to have t2 to be equal to c1 delta plus t1. So substitute solving for t1 c1, we are going to have c1 to be equal to t2 minus t1 on delta. So when you substitute back c1 and c2 into the equation we are having over here, we are going to have this solution over here. Okay, so looking at this solution over here, we can see that the temperature distribution is what? Is linear. Are we okay? I mean, I just have it here.
Look, I'm about to restart it for it to work.
Okay, so please, are you getting how the solution goes? All right, so we can continue. Okay, so from the Fourier's law, we know Q is equal to negative Ka dt on the x. So the T here represents our temperature difference, and the dx here represents um, the thickness. The x here represents the thickness, which is the delta we are having over here. So our temperature difference becomes our T2 minus T1. Then when you rearrange this, you are going to get this term over here. So from the Fourier's law, you are going to have Qx to be equal to, that is the heat transfer in the x direction is equal to Ka on delta multiplying T1 minus T2. Yeah, so if they ask you to find the heat flux, they are simply asking you to divide this equation by the area, dividing both sides by the area. So when you divide both sides by the area, you are going to get the left side of the equation to be the heat flux, which is mostly represented by Q prime prime. So this Q prime prime represents the heat transfer that is being transferred over the area. Yeah. Okay, so the heat transfer the Q can also be represented in terms of the driving force over the resistance. The driving force over the resistance. So when it comes to heat transfer, our driving force is the temperature difference. Because if there is no temperature difference, there won't be heat to be transferred. So the temperature difference represents our driving force in this instance. So writing it in this in that format, we are going to have the heat that is being transferred to be equal to the temperature difference over the resistance we are having here. So comparing these two, comparing this equation over here, the delta T on the R2, what we are having here, comparing this term to this over here, you can see that our R becomes delta on Ka. The R becomes delta on what? Ka. That's when you compare these two equations. Okay, so this one we have a single plane wall or a single slab. So we can have slabs in series. That is having them two or more. So in a case when we are having them in series, that's when you have composite walls. We are going to consider the heat that is being transferred in each of the walls. So doing that, you have to identify the thickness of each wall. So in that case, assume you're having three walls over here. We have the thickness of the first wall to be delta 1, and the thickness of the second wall to be delta 2, and the thickness of the third wall to be delta 3. And each of these walls are going to have their respective thermal conductivities and the resistance that they are going to be offered when the heat is being transferred from one point to the other point. So considering the first slab, we have the temperature T naught, which is being reduced to T1. Then now T1 also reduced to T2. Then T2 also reduces to T3. So is the heat the same heat that is being transferred through each of the slabs? So we can say that the heat transfer in the slab 1 is equal to the heat transfer in slab 2, which is also equal to the heat transfer in slab 3. Alright, so making everything simple, we can represent that in the table we are having over here. So considering the first slab, we have our temperature difference 1 delta T1 to be equal to T naught minus T1 as said earlier on. Then we have delta T2, we have this term over here, then delta T3 also, we have T2 minus T3 over here. And we can also consider the overall heat transfer. So in this case, considering the overall, we are going to add the temperature difference here to this and also to this. So adding these three temperature differences together, we are going to have T naught minus T1 plus T1 minus T2 plus T2 minus T3. So we can rightly see that the T1 here is going to cancel this T1, then T2 you're going to cancel T2 over here. They only have T naught minus T3 over here. So when you consider the overall temperature difference, our change in T, which you are having over here, will be equal to T naught minus T3. Alright, then we can also consider the resistances in each of the walls. So we have from this point we know our R, which is the resistance, is equal to delta on what? Ka. So when it comes to the first slab or the first wall, we are going to have our resistance 1 to be equal to delta 1 on K1 A. Then we have R2 to be this, then R3 to also be this. Then in this case, the heat that is being transferred in each of the slabs is going to be this over here. Then when we make our temperature difference the subject, we are going to have Qx multiplying the resistance over here. That's when you make change in T the subject over here. We have R multiplying Qx. So that's what we are having over here. Okay, so the overall resistance is also going to be the sum of all the resistances in the slab. The sum of all the resistances in the slab. So we add this resistance to this and also add this to this, and that gives us the overall resistance in this composite material over here. Okay, so when you do that, we are going to have our Qx to be equal to changing T over RT, which is represented by R1 plus R2 plus R3, and that is equal to the overall temperature difference over the sum of all the thermal resistances. Okay, so what this is just telling us is that it's not all instances that they are going to give you the temperatures at the various walls, but they can give you the temperature at this surface and also give you the temperature at this surface. So having the temperature at this surface and this surface, you can equally calculate the heat that is being transferred. And if they ask you to calculate the temperatures at the inner surfaces, you can also do that, because now you have the overall heat transfer, which is equal to the heat that is being transferred in the individual slabs. Okay, so when you rewrite this, we can have our heat transfer to be in this format. Then this represents our resistance and this represents our overall heat transfer. Alright, then we can also have the overall heat transfer coefficient. So finding the overall heat transfer coefficient, we assume that we have a hot fluid at one surface, which is so we have a solid wall over here, and this wall we are having here, the heat is being the heat that is being transferred through it is from a hot fluid we are having at this surface over here. So since the hot fluid is losing heat to the wall over here, the fluid that is going to be here is going to be the cold fluid, which will have a lower temperature as compared to the hot fluid. Okay, so in this stance, you can consider the heat transfer over here in the hot fluid. They also consider the heat transfer in the solid wall, and also consider the heat transfer in the cold fluid. So when they come here to um, evaluate the heat that is being transferred here, we consider the Newton's law of cooling, because this is convection. Then when it comes to the wall, we consider the Fourier's law, because this is a solid surface or a solid material. So the heat that is being transferred here is conduction. Then when it comes to the cold fluid, this also heat transfer by convection. So we consider the Newton's law. Alright, so the Newton's law states that Q is equal to um, the heat transfer coefficient H multiplying the area multiplying the temperature difference. So this is the Newton's law of cooling. The heat transfer coefficient. So the H here represents the heat transfer coefficient. Then we have our surface area over here. Then we have our temperature difference over here. Okay, so when you take the hot fluid over here with a heat transfer coefficient to be H hot, our temperature difference here is going to be the T hot and the T1. That is the then when it comes to the wall, our temperature difference is going to be T1 minus T2. Then when it comes to the cold fluid, our temperature difference will be the T2 minus the T cold over here. So considering the overall temperature difference over here, we are going to have T hot minus T cold. That is when you consider the resistances offered by each of them. So the hot fluid is going to offer some resistances. Then the wire is also going to offer some resistance, and the cold one is also going to offer some resistance. Okay, so when you add all the resistances together, then consider the temperature difference, the overall temperature difference to be equal to Qx multiplying the overall resistance. We are going to have our overall temperature difference to be the T hot minus the T cold. As we've seen when we're doing the composite material over here. Okay, so for the hot fluid, we are going to have our temperature difference one to be in this format. Then we have our K multiplying this, which means that the term here represents our resistance offered by the fluid. That is between the fluid and the surface. Then when it comes to the plane wall aspect, we are going to have our temperature difference to be equal to Q multiplying delta on Ka, which means that this represents our resistance. And when we go to the cold fluid, our temperature difference becomes T2 minus T cold, which is equal to Q multiplying what we are having over here, which means in this case, this term represents the resistance in that fluid. Okay, so taking all these three resistances together, we can have the overall resistance that is being offered when the heat is being transferred from the hot fluid from that surface to the other surface. Okay, so that's what we're having over here. So this whole term represents our overall resistance, which is RT. All right. Okay, so making Q the subject from this relation, you are going to have Q to be equal to T hot minus T cold over the total resistance. So when you factorize the area out in this and divide through by area, we are going to have Q on A to be equal to T hot minus T cold over 1 over H hot plus delta on K plus 1 over H cold. So doing that, whenever we have Q on the area, it means you are finding the heat flux. So they can equally ask you to find the heat flux from this term over here. Okay. Alright, so it is convenient to express the heat transfer rate in terms of an overall coefficient that account for both convection and conduction resistances. So in this case, you are going to have Q to be equal to UA um, multiplying T hot minus T cold. Alright, so when you compare this equation to this equation over here, we can see that the Q here will cancel the Q here. Then the temperature difference here is also going to cancel the temperature difference. Then our area here is going to cancel the area, because when you factorize the area out over here, this area is going to cancel that. Then we have our U to be equal to 1 over H hot plus delta on K plus 1 over H cold. These are some of the things I wanted to write, not to just show them. First of all, let's reduce. Okay, so this is what I was saying earlier on, that when you compare the two equations, you are going to have our U to be equal to this term over here, which is equal to 1 over A multiplying the term over here. Alright, so the R1 plus the R2 plus the R3 represents the total resistance, and that is for a plane wall. So you can equally have this also in the cylindrical geometry system. So in that case, you are going to consider a cylinder with a radius r here. So writing the general conduction equation in the cylindrical coordinate, we are going to have this whole equation over here. And remember, our assumption states that we are considering a steady state, which means the accumulation terms here goes to zero. They also consider isotropic material, which means that our K, rho, Cp are also constant in every direction. They also consider only the radial direction. So in this case, we only consider the radial direction. Okay, so we have our term here going to zero. Then we have the z term also going to zero. This is the radial direction term or the radial direction over here. Then we have this and this term over here. So because you are not considering those terms goes to zero. Then we are also not considering heat production or heat generation. So our term here goes to zero. So we only have zero to be equal to this term over here. And this is still the Laplace equation in the cylindrical coordinate or in the cylindrical geometry system. Alright, so the same thing happens. This is a differential equation, so there's a need for us to solve the differential equation to get the temperature distribution. So the first thing you have to do is to integrate this term over here. So integrating the term over here, we'll get this term over here, the term we are having over here. And then when you further integrate this term over here, we are going to have this term over here. So to solve for the C1 and the C2, you need boundary conditions. So at the initial stage when so the boundary conditions that you can make is that when r is equal to capital R1, we are going to have our t to be equal to t1, and when r is equal to r2, we have t to be equal to t2. So you solve for C1 and C2, then you substitute them back into this equation, and that will give you your temperature distribution to be equal to the equation we are having here. And when you rearrange,
What is?
Song, do you have a question?
Need this, we need song.
Hello, can you mute yourself?
But I haven't.
Song, please can you mute yourself? Okay, so when you rearrange the temperature terms over here, you're going to have this term over here. Not at next stage, but then it signifies. Okay, so when you consider the Fourier law, we are going to have QR. Full cycle from its humble beginning in tropical field to its widespread record.
Emmanuel, kindly mute yourself. Please, guys, let's all mute ourselves so that we don't distract the class. Okay, thank you.
Alright, so QR is equal to negative K on delta T delta R. Okay, so when you compare this equation From the first integral that we did over here, okay, so when you consider the first integration that we did over here, we can see that the t, the r will be equal to c1 on r. So when you substitute that into this equation, we are going to have, and knowing c1, we are going to have the t, the r. Okay, sorry, the t, the r is equal to c1 on r from the first integration, and we've solved for c1 to be equal to t1 minus t2 on ln r1 on r2. So when you substitute the c1 in here, we are going to have the t, the r to be equal to this whole term over here. Then when you substitute this term into the Fourier's law, we are going to have our KR to be equal to this term over here. And we should note that we are considering the surface area. So our area is equal to pi dl, and the d here is equal to 2r. Okay, so when you substitute that into the dt, the r, and the area into this equation, we are going to have the heat transfer to be equal to this term over here. Then when you further simplify it, we have this term over here. Then our term here is represented by the temperature difference. Then considering the driving force over the resistance, we are going to have the T, delta T on what, RT. So when you compare this term to this term over here, we are going to have our resistance to be equal to ln R2 on R1 all over 2 pi KL to be our resistance. So that is for when we have a single cylinder. That's when we have a single cylinder. We have our resistance to be this, then our heat transfer to be equal to this. So in a case when we have a composite cylindrical walls, we are going to consider the resistances in each of the walls as the way we did the plain wall. So considering that, we consider the temperature distribution in each of the walls, then the thermal resistances. So our thermal resistances are going to be this. Then the overall thermal resistances is going to be the sum of all these three resistances. So when you do that, substitute that into the heat equation, which is the driving force over the resistance, we are going to have our QR to be T1 minus T4, because our initial temperature here is T1 and the final temperature here is the T4. So we have this over here. So this is the resistance offered by the first one, this is the second one, and this is the third one. Okay, so we can also express this in the overall heat transfer coefficient format. So in this case, we are going to consider the same thing. So we have our hot fluid inside the cylinder, then we have our cold fluid flowing at the outside surface, then we have the thickness of the cylinder over here, which in this case the heat that will be transferred through it will be the conduction. So the heat transfer inside it will be the convection, and the heat outside there will be also be convection. So we consider the Newton's law and also the Fourier's law. Okay, so taking the idea from the resistance that you got from the plane wall when you're finding the overall heat transfer coefficient, you got to realize that The resistance offered when you have convection is what? 1 on each multiplying the area. So when you consider the hot um, fluid in this instance, you are going to have 1 over HI multiplying AI, where the AI represents the inner surface area and the HI represents the heat transfer coefficient inside. Okay, they also have the resistance offered by the thickness of the wall to be in this form. They also have the resistance offered by the cold fluid, which is 1 over H naught multiplying A naught, where the A naught here represents the outside surface area. Okay, so when you do that and substitute that into the driving force over the resistance equation, you're going to have this term over here. Then when you compare um, this equation to this equation over here, we are going to have our QR cancel the QR over here, our temperature difference cancel itself over here. Then we have our UA to be equal to the remaining term over here. So when you do that and simplify everything, we are going to have our U to be equal to this over here. So the U naught over here represents the overall heat transfer coefficient based on the outside surface area, and you can also write it in terms of what the inside surface area, and in this case it's going to be UI. So you have to take note of this if they ask you to evaluate the overall heat transfer coefficient given the parameters. Okay, so we also consider the critical thickness of insulation. But then we have an equation. Okay, so if there is no question, then we continue. All right, so when you add insulation to a material, there are two things that can happen, or there are two effects that that insulator can cause. One of them is to increase the resistance to conduction, and the second one is to decrease the resistance to convection, because the outer surface area for convection is going to increase. Okay, so let's consider a tube with an insulation. So the outside um, resistance is the R naught with temperature T naught. Then we have our insulator with the radius R INS. So the radius of the insulator is from this point to this point over here. So the thickness of insulation is going to be from this point to this point here. Okay, so if you have the thickness and you have the outside radius of the tube, you can find the radius of the insulator. Okay, so our T naught represents the outside tube wall temperature, R naught represents the outside tube radius. Then the T infinity we are having over here, assuming there is a fluid flowing around the surface of the insulator, we have our temperature infinity, which represents the ambient fluid temperature. So the heat lost, the overall heat lost here is going to be Q to be equal to T naught minus T fluid, T infinity over the overall resistance. So because you are having a fluid over here, because you are having a fluid flowing around it, we are going to have resistance by convection, also have resistance by conduction as a result of the insulator. Okay, so because the insulator is adding a certain thickness to the tube, the heat that is being transferred through the insulator is going to be conduction. Then the heat around it is going to be convection. So in a case where there is no insulator, it means you are only having the tube. So in this case, it's only the heat that is being uh, offered by the fluid around the tube that you are going to consider, because there's no fluid inside the tube. So you only consider the fluid around the surface of the tube. So in this case, there won't be any resistance that is going to be offered by the thickness of the insulator, because there's no insulator in this case. So we only have our Q to be equal to T naught on T infinity all over 1 over H naught A naught. Okay, so this is from this equation over here. When I rewrite this in terms of the driving force over the resistance. Okay, so if they ask you to evaluate, if you have a case in this form and they ask you to evaluate the heat lost without insulation, this is the equation that you are going to use. And if they ask you to evaluate it when there is insulation, then it means you are going to have the insulator resistance to it, which will make the resistance to have two terms in this instance. Okay, so for if insulation is being added to it, we are going to have our total resistance to be this term plus this term, and this term represents the resistance as a result of the fluid flowing around the outside surface of the material. Then this is the resistance offered by thickness of the insulator that is being added. Okay, so when you substitute that into the Q equation, you're going to have this equation over here. So if there is an insulator that is being added to the material, then it means this is what we are going to use to evaluate the the heat that is being lost. So to know whether the insulator is increasing the resistance to conduction or decreasing the resistance to convection, you compare uh, the values of the heat lost when there is insulation and when there is no insulation. Okay, so another term that we can also encounter is the critical insulation radius. So the critical insulation radius okay, so the critical insulation radius or critical insulation occurs when we have the maximum heat lost or when the thermal resistance is what minimum. So in this case, delta RT on delta R insulation is equal to 0, or delta Q on L on delta R insulation is equal to 0. So solving this equation over here, this differential equation over here, you're going to have this whole term here to be equal to 0. Then we can see that we have common terms over here. Okay, so we have common terms over here that we can factorize. And when we factorize that out, we are going to have this term over here. And because we are equating it to 0, the insulation radius here become the critical insulation radius. Alright, so when you have this term over here, it's either this term here will be equal to 0, or the term in the bracket here will be equal to 0. That will make this entire thing to be equal to 0. So considering the term in the bracket over here, considering this term over here to be equal to 0, we are going to have 1 over k to be equal to 1 over h naught multiplying the critical insulation radius. So making the critical insulation radius the subject, we are going to have k on what? H naught. Okay, so what will the critical insulation radius tell us? If the insulation radius is less than the critical insulation radius, then it means that adding insulation increases the heat transfer. Then in the case of a thick bare cylinder, if the uh, outside radius the outside radius is greater than the critical insulation radius, then it means that the addition of insulation will always increase the insulation effect. And if you have a thin bare cylinder, and this way, if you have the outside radius being less than the critical insulation radius, then it means that the addition of the first layer of insulation will decrease the overall thermal resistance, so enhances heat transfer, not insulating until the R insulation will be greater than the critical insulation radius here. Okay, so all what you have been doing initially is when there is no heat generation. So there will be some. Okay, so what we did here for cylinder, and when we have a sphere, we just multiply the critical insulation radius of the cylinder by 2 to get that for the sphere. Okay, so considering heat being generated in a slab, the walls of the slabs are kept at the same wall temperature TW, which are constant. We place the coordinate system in the center of the line, so we have our coordinate system here in the center here, which means that from this point to this point to become negative x, then from here to here become positive x, then from here to here is what? 2 times the delta, which means that we have delta here, then also have another delta over here. So adding these two deltas together, we are going to have 2 delta over here, 2 times the delta over here. Okay. Alright, so the assumptions you are going to make here is that this before then this point is going to be our maximum temperature that can be reached, and this the TW here represents our surface temperature or the wall temperatures. So the assumptions you are going to make is that there is uniform constant heat generation in the wall, and the unit of the heat generation is watt per meter cube because it's per volume. They have one-dimensional heat flow only in the x direction. They also consider isotropic material, then steady state conditions. So doing that and simplify the general heat transfer coefficient or the heat transfer equation for conduction, we are going to have the Poisson's equation. So this term goes to zero because we are considering steady state. Then we have these two term goes to zero because we are considering that one dimension. So we only have these two terms over here. These two terms over here. Okay, so when I simplify, we are going to have this equation which will represent the Poisson's equation. So we can solve this equation over here using the boundary conditions. So the boundary conditions here we have at x is equal to delta, that is from this point to this point, we have t to be equal to okay, Maxwell, you can have your question. Maxwell, you can ask your question. Maxwell, are you there? Okay, I think we can continue.
Hello.
Yeah,
Yeah, I've sent the question at the comment, please.
okay.
So it was will increase in radius increase or decrease the heat transfer, and then why?
Is it a composite element? Or is it
I think insulation.
insulation? Is it a critical thickness of insulation? Is it a critical thickness of insulation?
Yeah.
I think I can. Maxwell.
Hello.
Maxwell. So if you increase the insulation on the material, what happens is that you are going to increase. If you increase the radius, right, you are going to increase the surface area it will have. And when the surface area increases, then you can increase heat transfer by convection, right? But then you're rather reducing heat transfer by conduction. So there's a point you get to where we have the critical thickness, the critical radius, I think it's the critical radius of insulation also,
Yes.
right? When you are at that value, that's where you can have the maximum heat transfer being done. If you are too below that, or if you are below that value, you will have more of conduction heat transfer than convection. If you are above, you have more of convection than conduction. So the thing is that when you increase the radius, there is a point where the heat transfer generally is reducing because you are putting more material on it, right? But then it gets to a certain limit where if you should continue to increase it, now you are going to allow heat transfer by convection to happen more. I hope it makes sense.
Yes.
Okay.
All right. So what you were saying, it can be found here under the critical thickness of its insulation. Okay, so we continue. All right, so the second boundary conditions is when x is equal to negative delta, that is from this point to this point. We are going to have t to be equal to tw as well. So when it's up, using those two boundary conditions to solve for C1 and C2 and doing the substitution of C1 and C2, we are going to have our temperature distribution to be equal to this equation over here. And when we rearrange the temperatures, we are going to have this equation over here. So the distribution is symmetric about x is equal to 0. So at x is equal to 0, we have the t, the x to be equal to 0. That's when you look at the diagram, we can see that at this point x is equal to 0. At this point, we have x to be equal to 0. And when you come to the top here, you can see that it's at this point that we have the maximum temperature. It at when x is equal to 0 that we have the maximum temperature. So that's what they are saying over here. So in that case, you have the t, the x to be equal to 0. Okay, so when you consider the maximum temperature, that is t of 0, that at the point where x is equal to 0, we are going to have this term be reduced towards this equation, because this whole term goes to 0, the term here will go to 0. So if this term goes to 0, we only have these two terms over here, and our maximum temperature will be equal to that. So when we rearrange the temperature terms, we are going to have uh, this equation over here. Okay, so the temperature distribution can also be expressed with the maximum temperature, and that gives us this equation over here. Okay, so the total heat loss from the two surfaces at steady state is equal to the total heat generated, and that is equal to q prime 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 multiplying 2 times the area and the delta. Okay, so go through some few questions that will end the class for today. Then Friday, God will continue from the unsteady state heat conduction. um I wish I could solve the solution with you, but we have problem with our board, so I'll just take you through the solution. Then when I send the questions and you have problem, you can come to my DM for clarification, or you can enter our boss DM or Tilku's DM for more clarification. So we take our first question over here. Alright, so the question says that a firewall separates two rooms. In one room, a fire has started. The firewall is made of stainless steel that is 2 mm thick. Heat in the room is sufficient to raise the outside surface temperature of one side of the wall to 175 degrees C. If the thermal conductivity K of the metal wall is 20 watts per meter Kelvin and heat flux is 50 kilowatts per meter square, determine the surface temperature of the other side of the wall. Okay, so this whole problem can be illustrated in this diagram you're having over here. So one room we have one room at this end and have another room at this end, and this is the wall that is separating the two rooms, and they are saying this wall is made up of a metal which is stainless steel. Okay, so we have at this point we have fire that has started already. So this fire generates heat that is being transferred through the metal wall to the other room. So they're asking us to calculate um the temperature at this surface. Okay, and they have given us the heat flux. So since this is heat by conduction, we are going to use the Fourier's law to solve this problem. So we know from the Fourier's law, we know Q is equal to um, negative K A multiplying the temperature gradient, which is T1 T2 minus T1 over the thickness X. You can use X, or you can use the delta. Okay, so from here, when they give you the equation, the first thing you have to do is to write out your data from the equation. So from the equation, we have our thickness to be 12 millimeters, and we have temperature at one side of the wall to be 175 degrees C. Then we have our thermal conductivity to be 20 watts per meter Kelvin. Then our heat flux is 20 kilowatts per meter square. Okay, so since they've given us the heat flux and we don't know the area, we'll divide this equation through by what? The area, so that this term becomes what? Over the area. Then this term goes out. So you have negative K multiplying the temperature difference over the X. Our X here has been given, which is the delta, and our K here has also been given. So all you have to do is to substitute the values and find the unknown. So this is what you are looking for. Alright, so when you do those substitution, when you do that substitution and make T2 the subject, we are going to have T2 to be 145 degrees C. Please, are we okay with the solution? You can unmute yourself and give the answer. Please, are we okay with the solution? All right. Okay, then taking the next question, the question 2, a sloping roof Okay, so Makati, you are asking how will you know which is T1 and which one is T2, and the one you should subtract from the other. Okay, so when it comes to the first law, we have a negative sign here showing that there is heat lost when we are transferring the heat from one point to the other point. So you add if you include a negative sign in the equation over here, then it means you have to subtract T1 from T2, so that the negative answer that you get from T2 minus T1 will cancel this negative sign over here. But if you exclude the negative sign here from the formula, then it means you have to subtract T2 from T1. So in this case, it's going to be T1 minus T2. And T1 is always greater than T2. So if you exclude this negative sign from the formula, then it means you have to write the temperature difference in this format. But if you include the negative sign, then it means you have to write it T2 minus T1. Okay, so generally when I give you the equation where you have all the two temperatures, as I said earlier on, T1 is always greater than T2. Okay, so in this case, they have given us only one temperature and they are asking us to determine the second temperature. And they are saying that okay, so in this case they are saying that um, they are saying in one room a fire has started. The fire is made up of stainless. Sorry, the firewall is made up of stainless steel, which is this heat is heat in the room is sufficient to raise the outside surface temperature of one side of the wall to 175 degrees C. So when you take this equation, you can see that the fire is in the room one, the first room, and it's the fire that is going to generate the heat. So that heat that is being generated will raise the temperature of the wall that is close to it. So in this case, the side of the wall that the heat was raised, the heat was used to raise its temperature is going to be the surface 1 over A. So in this case, you are only going to think about the temperature at the other surface of the wall. Makati, are you okay? Makati, are you okay? All right, so I think we can continue. Okay, so a sloping roof of a house receives energy by radiation from the sun. Okay, so this is a convection heat transfer problem. The roof surface reaches a steady uniform temperature of 60 degrees C and the ambient air temperature um, is 30 degrees C. The roof dimension are 10 by 10 meter by 6 meter. Then the heat transfer coefficient can be taken as 10 watt per meter square Kelvin. Determine the heat transferred by convection to the air. So from the Newton's law of cooling, we are going to have Q to be equal to HA multiplying the temperature of the wall minus the temperature of the fluid. Okay, so they've given us the temperature of the fluid to be 30 degrees C and the temperature of the wall to be 60 degrees C. Then we have our dimension of the roof, which is 10 by 6. So we can find the area there. The heat transfer coefficient has also been given, so you just have to substitute and find okay. Okay, so let's take our third question. A cost a cold storage warehouse is to be constructed of a number of individual rooms that are maintained at various temperatures. The wall of one room are constructed of 100 mm brick on the outside and 12 mm thick plywood on the inside. Then sandwiched between the brick and the plywood is glass fiber insulation that is 87 mm thick. The inside wall temperature is to be maintained at negative 24 degrees C and the outside temperature is 21 degrees C. Determine the heat flow through the composite wall per meter square. Then you also determine the surface temperatures. Okay, so the problem here has been illustrated in this diagram. So we have our temperature, our heat over here that is being transferred from this point to this point. So we have our T naught here, T1, T2, T3 here. So in this case, they have given us T naught to be 21. Then they have given us T3 to be negative 24. Okay. And when the question is given, if you can write, if you can put the equation in the diagram form, that is good. But if you can't, it's good you leave it like that rather than going to draw a wrong diagram. And one thing to when we are solving, you have to indicate your coordinate system that you are using. Whether you are using your x, y, z in this format, the direction you are using for the x, or you are using your x in this format, it's necessary. So you have to indicate your coordinate system. If you are moving in this direction, it means the x is going to be negative. So if you are using this to be your positive, you are using this to be your positive x direction, then it means when you are moving in the right direction, your x will be negative. So since we are using this as our system, moving to the right means our x is going to be positive, and moving to the left means our x is going to be negative. Alright, so we are assuming our area is 1 meter square. Okay, so the first question asks us to determine the heat flow through the composite wall per meter square, which means we are finding the heat flux. So we use the Fourier's law to evaluate this problem because it's heat transfer by conduction. So we have our Q to be equal to K multiplying T1. Okay, so in this case, we are going to consider the overall heat transfer. So you consider the overall temperature difference, and the overall temperature difference is going to be T naught minus T3. So you have T naught over here minus T3 over the thickness. So we are determining our heat flux, so this should be per area. Okay. Okay, so we have the thermal conductivity of the brick, the thermal conductivity of the fiberglass, then we have for that of the plywood as well. So this is the brick, this is the fiberglass, and this is the plywood. Okay, so you can also write the okay, so we know that this is equal to the temperature difference, which is T naught minus T3 over the total resistance RT. Okay, so this is equal to this, and we know how to find the resistance when we have a plain wall. So the total resistance is going to be the resistance in the brick plus the resistance in the glass fiber, then the resistance in the plywood. Okay, so how do you find the resistance? We know our resistance is equal to delta on K. Delta on K. And you have the K for each individual plane. We have that for the brick, the glass, and the plywood. And also have the various thicknesses for them. So you can just find the resistance for each of them. Then after that, you find the total resistance. Then you know your T naught, you know your T3. So from there, you can get your heat flux over here. Then after getting your heat flux over here, now you can find to get the temperature T1 and temperature T2. You can now consider the heat that is being transferred through the brick and also the heat that is being transferred through the plywood or the glass. Okay, so knowing that, taking the brick for instance, our Q is going to be the K multiplying the temperature difference, which is T naught minus T1 over the resistance, over the thickness. So we know the thickness, we know our K for this, we know T naught, we know the heat that is being transferred. So the only unknown here becomes T1, so we can evaluate that. And when you consider the plywood or the glass, we can equally find T2 as well. So when you go to the solution, that's what they are practically doing. So our parameters or our data has been drawn from the equation. We use the driving force over the total resistance to find our Q, which is this over here. So finding the resistances in each of them, the heat in each of them, we are going to have these terms over here. So this for the brick, this for the fiberglass, and this for the plywood. Then we know that it is the same heat that is being transferred in each of the materials. So you're going to have this relation over here. Finding the resistances in each of the materials, we have this, and when you sum them up, you have the total resistance. And finding the overall temperature difference, you are going to have T naught to be equal to T3 and substitute into the driving force over the total resistance, we are going to have our Q to be equal to this. Then afterwards, you can now find our T1 and T2. Then after finding T1, we are going to have our T1 to be equal to 18.5 and T2 to be equal to um, negative 22.27 degrees C. Okay, so our time is fast spent. We are going to have end the class here, and I'll send you the questions for you to try. Then after solving, you can reach me out if you have any problem or any challenge. All right, you are all welcome.